Welcome back to Elementary Statistics. In this video, we want to develop a better understanding of the normal distribution. If you remember, we've talked about the normal distribution previously when we were describing the shape of a histogram. And because I'm lazy, I'm going to draw these as frequency polygons instead. We classified a distribution based on its shape. If there were low outliers, like we have in this first picture, we said that this graph had a negative skew. If there were high side outliers, like you have over here, we described this graph as having a positive skew. And the graph in the middle, which is very much symmetric over some central point, we said has no skew. And we said that's also called normal. Right? So that's what we're looking at when we're talking about a normal distribution. We want to study graphs that have this kind of a shape. So some key features that we can see in this graph. It is symmetric about the mean. There's an average value where I have the dotted line drawn, and the graph looks very similar on either side of that. The normal distribution is often described as being a bell-shaped distribution. It has a central peak and it tapers off in each direction. Those two ideas combined, because it is symmetric about the mean, that forces that the mean is equal to the median. Right? There have to be the same number of scores to the left and right of the mean in the distribution in order for it to be symmetric. And the median is the point where the same number of scores are to the left and to the right. Because that symmetry, that peak happens in the center. The peak is the mode. So the mean has to equal the mode. That is a requirement of these two properties. Compare that to some of the other graphs we've looked at. The mean, the median, and the mode of these distributions are going to be spread out. The mode is going to be way off on the side where the peak is. The mean is going to be drawn heavily towards those outlier scores. The median could end up in a couple of different places, but generally in these pictures, we expect that it's somewhere in between the two. So there's one of the reasons that studying the normal distribution is so useful, is just for the sake of simplicity. Normal distributions give us nice data. They give us a nice thing that we can analyze without all that much complication. We'll see in a little bit later that the normal distribution is actually far more important than that. it turns out that under certain conditions, a normal distribution is almost inevitable. Everything becomes a normal distribution if you analyze it correctly. And so there's something to look forward to, but for right now, just a normal distribution is a nice distribution. It has some well-behaved properties that make it easy to study, so that's why we're going to study it. In order to talk about the distribution, it makes sense to have some tools for making predictions about the distribution. That is to say, our next goal is to look at a normal distribution and ask questions like, how many scores fit into this part of the distribution? Or, a little bit more specifically, how many scores are there lower than the score that I care about? Answering that question gives us the percentile rank of that particular score. In general, to answer this question requires the study of calculus, and I do not expect that students in this course have taken calculus yet. So we're going to shortcut the calculus by using what's known as the standard. Normal distribution. The standard normal distribution has a mean 0 and has a standard deviation 1. We're generally going to think of the standard normal distribution as being a population distribution. So that would be, right, mu equals 0 and sigma equals 1. But we're not necessarily going to require that. So I'm just using the words as well, mean and standard deviation. The standard deviation is very convenient because mathematicians have studied it extensively. And there are tables of data available where other mathematicians have calculated all of the values that go into it. So you don't need calculus. You can look it up in a table if your data is in the standard normal distribution. It has a mean of 0 and a standard deviation of 1. It turns out that there is a really nice transformation between any normal distribution and the standard normal distribution. It is called the z-score. So the standard normal distribution is sometimes also called the z-distribution, because if you have a known z-score, that takes your score from any distribution you are studying into the normal distribution. So let's say that you have a distribution. You have a score, you have a mean, you have a standard deviation. We know that you can take your score, you can subtract the mean, and you can divide by the standard deviation to get the z-score. I'm not worried about that part of it. I trust that you know how to do that much of the process already. What I'm interested in it is what happens when we have that z-score. And the answer to that question is that we go to what's called the standard normal cumulative probability table. This is sometimes called the standard normal distribution table or the z-score table. There are two of them. The one that I have on the screen right now is for negative z-values. And if I scroll down off this page and onto the next page, we have positive z-values. Reading these tables is not immediately straightforward, but with a little bit of practice, it becomes pretty easy. In our case, we are looking for the z-score of 1.36. In the column marked Z, if you scroll down far enough, you will find 1.3 showing up here. I really wish I could get that to stop popping up every time I highlight something. But in order to condense things, instead of going through every digit, we go across the page. So that row that is marked 1.3, the first score is 1.30, 1.31, 1.32, 1.33, 1.34, 1.35, and here is 1.36, 0.9131. I can come back to my work and write down on the table A is 0.9131. Turning this number from a decimal number into a percentage a z-score of 1.36 corresponds to a score in the 91st percentile. Another way of saying exactly the same thing, there is a 91.31% chance that a randomly chosen score in this distribution is lower than yours. I'll put yours in quotation mark because whatever score this z-score came from is the interesting question. So there are two things that we can talk about. We can talk about a z-score as a tool for finding a percentile rank. We can talk about a z-score as a tool for finding a probability. Once we're talking probability, we can get to be a little bit more interesting. What is the probability that a score falls between z equals positive 1.00 and z equals negative 1.00? Now, if you remember, the standard normal distribution, the z distribution, has a mean of 0 and a standard deviation of 1. So this question is actually asking us, in any normal distribution, what is the probability that a score falls within one standard deviation above or below the mean? And we can answer that question by going back to our z-score table. If I can hit the right button, 1.00 corresponds to an area of 0.8413. And if I scroll back up, the negative z-scores on the table, negative 1.00 corresponds to an area of 0.1587. That's really all I need. You do a couple of these in practice and you will start to really get comfortable with it. But for the first few, I'm going to draw out what these things mean on a standard normal distribution. So if I pick z equals 1 right here, the portion of the distribution to the left of that, all of this space, is 0.8413. Or again, thinking about that as a percentage, 84.13% of all of the space in the distribution, all of the area under the curve on the histogram is in the blue shaded region. Then if I graph z equals negative 1, and my negative got lost when I wrote that down over here. Sorry about that. When I put in z equals negative 1, that gives me the area of all of this. The question is asking me, how much space is that much taking up? Everything that we care about is in the blue region, but some of the blue region is out of where we care about. Conveniently, all of the stuff that's out of what we care about in the blue region is also in the yellow region. So if I subtract these areas, I get 0.6826, 68.26%. So there's my answer. There is a 68.26% probability that a score falls between those 2 points on the z distribution. Let's say now that we want to find a z-score so that 11.5% of all scores are above that score. This one is tricky in a couple of ways. First of all, we are given not a z-score, but an area. Second of all, it's not the area that the table tells us about. The area that we are given is over here. 11.5% as a decimal is 0.115. To do anything with this on the z-score table, we need the area over here. To figure that out, I'm going to rely on the fact that 100% of the distribution is in the distribution. If 100% of the distribution is in the distribution and 11.5% of the distribution is outside of the area we care about, we can subtract those things either as percentages or as decimal numbers, whichever makes you happier, to get the value that we need to find on the table. 1 minus 0.115 is 0.885. If I jump back to my standard normal distribution table once again, I'm going to scroll around looking for 0.885. Remember though, this time I have the area. So I'm not looking at the z-scores. I'm looking inside for 0.885 or as close to it as I can get. 0.8849 is really close. And reading off that 0.8849 occurs at the place where z is 1.20. So there we have it. I think that that's probably a good place for us to stop. Next time, we'll be looking a little bit more carefully at how we can use this. We'll look at the other steps of the process, starting with a distribution that is normal, but not the standard normal, using the z-score to translate between them and seeing where we can go from there. For right now, I'm going to wrap up. Thanks as always for joining me. I'll see you next time.